AI is shifting from passive prediction to systems that actively improve the data, the evaluation, and even the perception stack underneath the model. That matters because the next leap in capability may come less from bigger models and more from better synthetic training signals, better world model feedback, and visual representations that preserve geometry instead of just semantics. What connects these three results is a common push toward AI that learns from structure, not just scale. Keep watching, because the details show where current pipelines break and how researchers are fixing them. Let's explore the first paper, Autodata, an agentic data scientist to create high-quality synthetic data. Autodata, from Fair at Meta, is a general framework that turns an AI agent into a data scientist that iteratively creates, evaluates, and revises synthetic training data, then Meta optimizes its own prompting strategy. In the paper's agentic self-instruct implementation, a Kimi K2 6 orchestrator coordinates a challenger, weak solver, strong solver, and judge to generate examples that separate capability levels using Qwen 3 SAX 54B as the weak model and Qwen 3 5397B A17B as the strong model. On computer science papers from S2ORC, the agent needed 6.59 rounds on average to accept an example, and the accepted set shifted weak solver quality from 0.677 to 0.458, while raising strong solver quality from 0.696 to 0.772. Training Qwen 3 54B with GRPO on 1.3K. Agentic examples lifted held out mean at 3 from 0.63 to 0.774 on the COTI test, and from 0.366 to 0.632 on the harder agentic test. On legal reasoning from pile of law, the same loop reshaped weak rollouts from degenerate all zero outputs into a usable learning signal and GRPO training on 2. 8K agentic examples improve PR bench legal from 0.343 to 0.393 under Kimi K2. 6. Grading. Surpassing the larger 397B baseline at 0.358, in scientific reasoning over mathematical objects, agentic data achieved the best overall AVG at 8 on the combined validation set at 71.86%, and reduced truncation rates at a 65,536 token budget from 23.75% to 4.09%. A separate meta-optimization loop further raised the CS validation pass rate from 62.1% to 79.6% over 233 iterations. Let's explore the second paper. GigaWorld won a roadmap to build world models for robot policy evaluation. GigaWorld, one from Giga AI and Tsinghua University, reframes world modeling as a first-class problem for robot policy evaluation, where the goal is not photorealistic video synthesis, but agreement with real robot success and failure under closed-loop rollout. The paper introduces WM Bench, a benchmark built from 2,989 paired trajectories across 8 manipulation tasks, then studies 7 world models, 4 action representations, and 324,000 plus simulated rollouts to identify what actually predicts evaluator quality. The strongest signal is not appearance stability, but long horizon, action-faithful consistency. Subject consistency reaches 0.88 correlation with the world model as evaluator score, perspectivity 0.86, and instruction following 0.84. While background consistency and photometric consistency are negatively correlated at negative 0.45 and negative 0.42, on the modeling side, the best action interface is a pixel-aligned control map, which raises trajectory accuracy to 0.3528 and hierarchical memory dramatically improves 4.0. Second rollout quality, with GigaWorld, 1+ mem pushing PSNR to 19.82 and FID down to 40.58 from 14.05 and 142.84 in the memory-free baseline. After training on about 12,980 hours of mixed physical, robot, egocentric, and giga-collected data, GigaWorld 1+ reaches 0.6834 average score, outperforming Cosmos. Predict 2, 5 by 11.6%, and WAN 2.25B by 14.9%, while a LoRa-tuned Qwen 3 VL evaluator achieves 87.8% exact agreement and 0.7349 quadratic weighted kappa against human WMES labels. Let's explore the third paper, Vision Pre-training for Dense Spatial Perception. Vision Pre-training for Dense Spatial Perception proposes a boundary-centric self-supervised objective that treats boundaries as native learning signals rather than downstream outputs. Instead of random masking, the method uses masked boundary modeling. A teacher vision transformer discovers boundary-bearing tokens online, forces them into the student's masked set, and supervises them with a categorical boundary field loss over discretized distance and orientation bins. This reparameterization stabilizes dense self-distillation and enables parameter-free a contrario validation of candidate line segments, so unsupported structure never becomes a training target. Scaled to Lingbot Vision, a 1B vision transformer trained on 160 75M curated images, the approach matches or surpasses foundation models up to 7B parameters on dense spatial perception. On NYU Depth v2 linear probing, Lingbot Vision reaches 0.296 RMSE ahead of DNOF 3's 0.309, while on Davis 2017 and YouTube VOS, it posts 70 and 73.5 J and F mean, respectively, near the strongest distilled baselines. The paper also shows that a 03B student matches the 7B DINOV 3 on NYU Depth v2 with roughly 23 times fewer parameters. These pre-trained encoders transfer directly to Lingbot Depth 2, where replacing the initialization and scaling RGBD training data from 3M to 150M samples yields leading depth completion on 14 benchmarks, especially on hard, transparent, and reflective scenes. That's a wrap on today's AI paper highlights. Thanks for watching.